Hi, welcome back to my channel, and for today's video, we will be continuing with what we have started for the introduction of finite fields. Okay, so this time we will be talking about the construction of field extensions by adjoining elements. So for those who are new to my channel, please don't forget to click down there to subscribe so that you'll be updated on a lot of videos that I'll be uploading soon. And for those who have been here for a very long time, thank you so much for your undying support. So let's start now. So our discussion will be focusing on the construction of field extensions by adjoining elements. So by that, let's consider these as an example. So the field q of square root of 2. So how should we interpret this? Now take note that q here is the set of rational numbers, and this one here is irrational number. Okay, so this is the set of rational numbers, this q. Now, in order for us to see how does q of square root of 2 look like I mean the elements inside the set q of square root of 2 look like. So we need to make sure first how does the basis look like. Okay. Now, the basis actually here, the elements of the basis are actually of the form square root of 2 to the I, where your I is from 0 up until to where it needs to stop. So we don't know where it needs to stop, but technically the technique for that is you just have to look into this irrational number here, that's square root of 2, and take what is the nth root here. Observe that square root of 2, so that means the nth number is actually 2. So therefore we only have two values of I. So one is 0, the other one is 1. Why? Let's take a look into this. So our basis here would be 1, because it's supposed to be square root of 2 raised to 0, square root of 2 raised to 1. So that's technically the same as 1 times square root of 1 and square root of 2 rather. Now, why do we have to stop at 1, not on 2? Because if I'm gonna consider I equals 2, so that's gonna be squared of square root of 2, that's technically equal to 2. However, your 2 here can be written as a product of 1. It's already spanned by 1. So technically, our basis would only be 1 and square root of 2. And I hope you understood already what a basis is. I already have provided a separate discussion for that. I have uploaded a video for the basis of a vector space. So it's pretty basic here that we understood that the basis of this q of square root of 2 is this one here. Okay, so now that we know that this is the basis, then the set here for q square root of 2 is of the form a plus square root of 2b, where of course your a and b here are elements of rational numbers. Technically, because you're actually extending the set of rational numbers. So meaning to say that since the basis of q square root of 2 is 1 and square root of 2, then we can say that the degree of the q here over q, so basically you're actually seeing this perspective as a vector space over the underlying field. So technically q of square root of 2 is actually an extension field. So you can write this in this way. Is actually 2. So that's the dimension or the degree in this case. Okay, so the multiplication here works by this. Let's say you have a plus b squared of 2 times c plus d squared of 2. So this is technically the same as, correct me if I'm wrong, I would get in my own calculation as this. uh, AD plus BC square root of 2. Okay, so basically, remember that your A here, your B, your C, and your D are actually coming from your Q. And Q is already closed under addition and multiplication, so technically this is Q. This is also Q. And so this thing here is also an element of Q of square root of 2, implying that our Q of square root of 2 is closed under multiplication. How does it look like when you do this one? Square root of 2, that's B plus. So this is pretty simple. If you're gonna add that, you can just add A and C here. And this is already element of Q. You can also you also have here B plus D square root of 2, and this is already element of Q, implying that Q also is closed under addition. So another way of saying the perspective of this field is that what is really square root of 2? So square root of 2, remember square root of 2 is simply a root of the polynomial x squared minus 2. So so you have x squared minus 2. So if you're solving for x, you technically get x equals plus or minus square root of 2. So 2 here is a root of the polynomial x squared minus 2. 2 here is not an element of Q. So this means to say that this one here, this is monic polynomial in the sense that the leading coefficient of the polynomial is 1, and this is irreducible. I will provide a separate discussion for monic and irreducible polynomial for that. Okay, so since we know that square root of 2 here is actually a root of the polynomial x squared minus 2, then we can consider instead here this one x squared minus 2. So this is of the form you have, let's say you have a polynomial ring here, mod a polynomial, which is, in this case, this should be monic and irreducible. Okay, so you have this of this form here. In this case, this is isomorphic to q squared of 2 here. So which means to say that the ring where we adjoined a root of the polynomial x squared minus 2. That's it. So if you have any questions or clarification, you can comment down there so that I would know and we can discuss this thoroughly. So by this form here, so that's square bracket x over x squared minus 2. So this means to say that your q square bracket x is a polynomial with coefficients in q, and this notation here means that any polynomial f of x where we can replace x squared by 2. So by this, let's say if we have x cubed plus 2x squared plus 3, this would be considered equivalent to this. Remember, x cubed, I can write that as x squared times x. And I can 2x squared I can write as 2 times x squared plus 3. Now since we work under the this one here, and 2 square root of 2 is actually the root of the polynomial x squared minus 2, so we can have x squared equals 2, right? So basically I can replace this as 2 here. X, I can replace this by 2 so that I get 4 plus 3, and so I get 2x plus 7. That's it. Okay, so that means it has to be done when we work under the q bracket x square bracket x over mod the polynomial that has a root of square root of 2. If we are actually working on the extension field of q with adjoining a polynomial with adjoining a root square root of 2. So what does this imply? In this way, we can replace, okay? So we can replace any polynomial of degree 1 of the form a plus bx. Okay, so in other words, identifying x with square root of 2 gives the isomorphism of this ring. So I'm talking about the ring, the q square bracket x with the above field q of square root of 2. Okay, that's it. Okay, now for q squared of 2, this means to say that you know that the elements here is a plus 2 squared of sorry, b squared of 2, where your a and b here are coming from q. Okay, again, just to make sure, the reason again is that the basis of this field here is actually 1 and square root of 2. Now, my question is, do we have this one here? What if it's not a square root of 2, it's 2? So what could be our basis for q of 2? Now, let's try to check this. The basis is 1, of course. So because 1 can span anything, but we no longer have any basis because if you do the 2, that's already spanned by 1. So technically, the basis is a single tone containing 1, which in this case, our q of 2 is a here, where your a is coming from q. And technically, this only implies that q of 2 is equal to 2. Why? Okay, so you might want to pause the video first and try to think the answer for why is q of 2 is equal to q. Okay, so I think it's you have already paused these for a couple of seconds, but to answer on that, why the q is actually the same as q of 2, technically because remember that we're talking about the extension field. However, we cannot extend the q if in the first place, the element that we are going to adjoin to Q is technically coming from the Q itself. Remember, 2 here is a rational number. It's coming from Q. So how can we extend that set if the element that we need to adjoin them to be extended is on the same set? I hope you get what I mean. There's a difference. Q here is a rational number. Square root of 2 and 2 here are different numbers. Square root of 2 is irrational. 2 is a rational number. So if you're going to add 2 to that, nothing will never be affected. Like, there's no effect. in the sense that 2 is actually coming from that. Square root of 2, if you are going to adjoin that, then of course, the number of elements on that set will be added by 1 because you're actually adding square root of 2 here. That's it. Okay, so similarly, for q of square root of 3, so the basis here is 1 and square root of 3. Okay, why? Again, just to make sure, the nth root of square root of 3 is 2. So therefore, the I, wherein square root of 3 raised to I should only be 0. Your I should only be 0 and 1. So if you raise this to 0, you get 1. If you raise this to 1, you get square root of 3. Because if you raise that to 2, then you get 3, and 3 is spanned by 1. So technically, this is the basis of q square root of 3. So meaning to say that the elements of q here is a plus square root of 3b, where your a and b here are coming from rational number, the set of rational number. So this is quite isomorphic to q square bracket x. So we need to find a polynomial at which square root of 3 is actually the root of that given polynomial. So this is pretty obvious. You can have x squared minus 3. Okay, so let's check. This is monic. This is irreducible polynomial. So therefore, it satisfies. And so this is isomorphic to that. Okay, next. How about if our field here is the q of 7 to the 1/5. Okay, so let's double check the basis. Remember 7 to the 1/5, that's the same as fifth root of 7. So basically the basis for q of 7 to the 1/5 is you have 1, you have fifth root of 7. Okay, how does it look like, by the way? So you'll get fifth root of 7 to the I. So when I is 0, you get 1. When I is 2, so by the way, we need to have 5. Of course, we need to have 5 values of I in the sense that the nth root is 5. So here in this case, when I is 0, you get 1. When I is 1, you get fifth root of 7. Okay, I'm sorry. Why did I put close on this? I'm not done yet. Okay, here. When I is when I is 2, you get fifth root of 7 squared. When I is 3, you get fifth root of 7 cubed. When I is 4, you get fifth root of 7 to the 4. And let's stop it this way because there are already 5 elements of the basis. So which means to say that q of 7 to the 1/5 o mod I'm sorry, the degree of 7 q of 7 to the 1/5 over q is actually 5. So meaning to say that the elements of this is of the form a plus b fifth root of 7 plus c fifth root of 7 squared plus d fifth root of 7 cubed plus e fifth root of 7 to the 4th. And where A, B, C, D, and E are from Q. That's it. Okay, so last example is, how about this? Suppose our K here is Q of this one, where I don't know if this is psi or whatever. So psi of sub 3 is a primitive cube root of unity. Okay, so when this is a primitive cube root of unity, which means to say that your 3 here is actually 1. So basically, the basis is you have 1, you have 3, and you have 3 squared. That's it. And so the dimension or the degree of q of psi sub 3 over q is actually 3. And so this is quite isomorphic to q square bracket x over x squared. Let's try to check if that will work. X squared plus x plus 1. Oh no, it should be x cubed x squared plus 1. So let's try to double check if this is a monic irreducible polynomial. Okay, so the degree is 3 and that's correct. This is monic polynomial. Let's check if this is irreducible. X cubed is actually 1. That's x squared plus 1. Yeah, that's it. So that means there is no root here over q. So this will work. That's it. Okay, so that's all for now. Thank you so much for watching. So if you have any questions or clarifications, you can comment down there so that I would know and we can help you discussing about that. So up next, we will continue with the study of finite field extensions or the Galois fields. So if you have any concerns, clarifications, or questions, you can comment down there, and you can also comment if you would like to request a specific topic that you would like me to discuss on my vlog. So thank you, and I hope you enjoyed the video. Have a great day. Bye for now.